Good morning, everyone. Welcome to our lecture. Today, we are going to finish chapter 3 and start chapter 4. Uh, I did post a study guide for exam number 1, midterm exam number 1. You should pay attention to the study guide, what you need to focus on. The exam will cover chapter 1, chapter 2, and chapter 3. I prepared the practice questions and posted them in my lab and mastering. They are not going to count towards your final grade. They are designated as practice questions. So if you have studied the material and you think you have mastered the concept, you can go into the practice. It will not affect, or I will not use those practice questions towards your final grade, but it will help you to see or appraise yourself, see how well-rounded you are prepared to challenge the exam. I'll take note of, the statistics, see how many people are utilizing those practice questions so that in the future, if need be, I'll also make them available for midterm exam 2 and midterm exam 3. Nick is reminding everyone that there will be an SI support instruction exam review session tonight at 6 p.m. Please take note of that as well. Tonight, there will be a review session. Somebody is asking if I do have. Yes, I will also. Chapter 4 should be available. All the chapters, all PowerPoint slides for every chapter Trinity should be available. Should be available in the modules. All right. Please go to modules on Canvas and click the chapter. You will see the PowerPoint slide for each chapter.
It only goes up to chapter 3.
All right, let me just make sure that we are all on the same page. If you say chapter 3, let me see, maybe it's on my end that I didn't make them available. All right, let me just make sure that you can see it. All right, that is chapter 4. Slides. I thought I made that. Oh yes, you're right about that. Chapter 4. I also have the chemical, the solubility chart. I'll make other resources for chapter 4 available. So you should see 4. I can also make 5 available. You'll be able to see 4 and 5 now. You should be able to see 4 and 5. All right, just let me share my screen and we pick up from where we stop. Please show up tonight, 6 p.m. for SI session, support instruction session to review for exam on Thursday. I will, all right? I will also post a formula sheet and equations. If there are constants you will use, I'll make them available. You will see on the formula sheet and constant, which you should print before Thursday. I expect you to print the formula sheet. I'll also make that available today. By end of the day, I will share the formula sheets. At least you can have them ready along with the periodic table. Conini, you have a question?
Yeah, I'm not sure if you mentioned it earlier, but exam one is chapter one, two, and three.
Yes.
Okay, and it's not going to include anything from four.
Yes, whatever we'll cover the day for will not be there because you only have a short
Okay.
time to study, but it's going to be the quiz. So one, two, and three.
Okay, thank you.
All right. So picking up from where we stopped last time, we went as far as the limiting reagent and excess reagent concept. We looked
Professor
at,
Leggett, I just wanted
yeah.
to ask really quick. You just mentioned a constant sheet. So whenever you post or send that out, the constant sheet and the periodic table, those are two things that we're allowed to have during the exam, or is that just things that we need to prep for with the exam?
No, those are the things you will need along with the scratch papers, of course, for calculation and calculator.
Okay. Okay, good. Thank you.
Mm-hmm. And anything you'll need, I'll provide. So that is for exam one. If you just join in, I'll share today the formula sheet, which will have constant equations. You will also need the periodic table. So bear in mind, you will need the scratch paper as well and the calculator. So coming back to the concept of the limiting reagent, excess reagent concept, we defined last week the limiting reactant in a chemical reaction. I know it's more tempting to define a limiting reactant along the lines that it is present in small amount, because from the word limit, you may think it is present in small amount. Could be true, but not necessarily. The appropriate way or best term to define limiting reagent is a reactant that produce less amount of what? Less amount of the desired product. On my whiteboard, I'm using LR for limiting reagent, ER for excess reagent. And on the PowerPoint slide here, this is an equation, all right? This is an equation where iron 2 oxide react with carbon monoxide to produce iron and carbon dioxide. The question is, what is this is the question we looked at last time. I meant to say this, the equation here, zinc, 1 mole of zinc reacting with two moles of silver nitrate to produce 2 moles of uh, silver and zinc nitrate. This is the learning check problem we solved A last time, and this is the method or approach you will use to determine a limiting reactant in a chemical reaction. You assume one reagent is is the limiting reagent and determine how much of the desired product you expect if all the given reagent is consumed. And then you write down the amount, whether in number of moles or in grams, and then you write down. And then you take the second reagent, all right, and assume that it is the limiting reagent and determine how much of that desired final product will be produced if that unit is consumed completely. For example, here, we assume zinc is the limiting reagent. How much of uh, silver in this case, using the mole ratio, okay? The first conversion factor here is just converting the 2 grams to moles of zinc, and use mole ratio between silver and zinc and the mass of molar mass of silver to see how much in grams. Uh, the setup, okay? The setup you see here, unless you practice, you need to practice so that you know how to set up your equation. You may have the first setup correct, but if you flip the equation here, the 2 is below and 1 is above, you'll end up with the wrong answer. So make sure you reconcile the unit. You see how I'm canceling out zinc and zinc, grams of zinc, grams of zinc. These are moles of zinc, moles, remain with moles of silver. And then also we cancel with moles of silver. If I was to cancel moles of silver, we will cancel this and that moles of silver. We remain with grams of silver. You assume that. Then you take the second reagent and also assume that it is the limiting reagent. If it's a limiting reagent, how much of silver? You cannot change, okay? You cannot use the second product. You have to be consistent on which product you are using. I chose silver because it is in the subsequent question B here, we are asked how many grams of silver are formed. So I'm not gonna use that. And stands out that this is the amount of silver produced when all 2.5 grams of when 2.5 grams of silver nitrate are consumed completely. So the reagent which produce less amount of the desired product is the limiting reagent. At this point, I can say, all right, the limiting reagent is silver nitrate. This is the silver nitrate. And this is the amount of silver produced. I've seen questions where they are, or multiple choice is given in terms of silver is the limiting reagent and the amount of silver produced will be 6.5. You know, just to mess up numbers around, you have to be careful. If I look at the problem again, to go back to before we look at C, if I look at the top right here, silver nitrate, look at the silver nitrate. If you know the chemical formula for silver nitrate, for example, and you are expected to translate to chemical formula and then you write the balanced equation, it's gonna be a challenge. This is chapter 2, naming of ionic compound. So you are expected at this point to be able to write the correct chemical formulas. So the limiting reagent is silver nitrate. This is the limiting reagent. Silver nitrate is the limiting reagent. And the amount of silver produced is 1.5 grams. 1.5 grams. That is B, how many grams of silver are formed. Now, switching gears to product number 2 here now, look at this. All along, we use this to determine the limiting reagent, but in C, we are asked to find the amount in grams of zinc nitrate or zinc nitrate produced. So in this case, this is how you will proceed, having known or having identified the limiting reagent. We know the reaction will freeze over. It will stop once the limiting reagent is completely consumed. And this is our limiting reagent. So in this case, we will write down what we are given, 2.50 grams of silver nitrate. We will change that to grams of silver nitrate using the molar mass. This is the molar mass of silver nitrate, 169.87 grams of silver nitrate. You may be given the molar mass. If not, you will be required to use the periodic table to find the molar mass of silver nitrate. So this what I'm doing here is to convert the grams of silver nitrate to moles of silver nitrate. Next is the mole ratio between silver nitrate and zinc nitrate. The question is how are you going to set up your equation? If you look at unit cancellation, I'm remaining with moles of zinc nitrate, which means I'll need to cancel the moles of silver nitrate here I'm looking for moles of zinc nitrate here, NO3, with the 2 there. From the balanced equation, the coefficient for every 1 mole of zinc produce 2 moles of silver nitrate are consumed. Note that we didn't use this because this is an excess reagent. This is the limiting reagent, and this will limit the amount of either of these two. And part C, we are looking for grams of zinc nitrate. Unit cancellation, moles of silver nitrate, this is silver nitrate, moles of silver nitrate. We are looking for grams of silver nitrate. So 1 mole of zinc nitrate weighs 1, all right? Zinc nitrate weighs 189.36. This you can get from the periodic table. Zinc nitrate, grams of zinc nitrate, so that you cancel moles of zinc nitrate, and you end up with 1.8 mean 1.39, somewhere 1.39 grams of zinc nitrate. This is how much of zinc nitrate will be produced. Take note of the balanced equation. This is the mole ratio. And the last conversion factor is the molar mass of zinc nitrate. Do that. Express the final answer in grams of silver zinc nitrate formed. Lastly is how many grams of excess reagent are left at the end of the reaction. We know the excess reagent, the excess reagent here is zinc, and we started with 2.00 grams of zinc. Not all 2.00 grams will be consumed. Some will be left, and that is what question D is looking for. That's what you are being asked. This will call for, all right, this will call for determining how much of 2 grams are consumed when all zinc silver nitrate are consumed. So we'll set up the equation this way. This is D, 2.50 grams. This is the limiting reagent. We change to moles using the molar mass. This is the molar mass of silver nitrate, 87 grams of silver nitrate, NO3. I'm just using the molar mass of silver nitrate to change the 2.5 grams to moles. So that unit cancellation. Now the mole ratio here, mole ratio between excess reagent and the limiting reagent. Since I have silver nitrate here, I'm just going to cancel out moles of silver nitrate, moles of what? Moles of zinc. And the values, these are the coefficient in the balanced equation. For every 2 moles of silver nitrate consumed, 1 mole of zinc is consumed. How did I know that? 2 will be the denominator, the numerator is 1. It's based on what I do have here. Silver nitrate will cancel. Up to that point, I will only have moles of zinc consumed, but the question is excess reagent. The setup here is only giving me grams of zinc consumed. So I'll use the last conversion factor here. The last conversion factor here is to find the grams of zinc consumed using the molar mass of zinc, moles of zinc. And here, this is the atomic mass or molar mass of zinc, 39 grams of zinc, so that moles and moles will cancel out. And the grams consumed is 0.48 grams of zinc consumed. This is not what is left over. This means when all 2.5 grams are consumed, 0.48 grams of zinc are consumed. So the leftover excess, therefore, zinc is obtained by determining the difference, 1.48 grams, 1.5, 2 grams of zinc is left over after the reaction, Okay. These are the common, all right. These are the common problems you will come across in limiting an excess reagent. It will just revolve around what is the limiting reagent, how many moles of the limiting reagent are consumed, how many grams of the XYZ product is produced, and so forth. So any question, let me see my chat window here. Alexa, any question about, you have any question about, what you missed? I see you are asking that you had internet connection.
Sorry, I'm not sure.
Hello?
I have a question.
Yes.
Where did you get 0.48 again? Was it the equation that you just did previously?
Yes, from
Okay.
here.
Okay.
This
I
is,
just didn't get the end of it. Thank you.
all right, yeah. So what you see on my whiteboard is the setup to determine the mass of zinc consumed when 2.5 grams of silver nitrate are consumed. That means the limiting reagent.
Thank you.
Yes. Any other question?
Yes, I actually have one.
Yes.
So I just wanted to make sure, would you mind just explaining why you would use like the 65.39 grams of zinc rather than the 2 grams that they have in the actual problem?
Well, I'm using this one, like the last conversion factor here.
Mm-hmm.
It is the, this is the last conversion factor is that molar mass of zinc. It is just off the periodic table, because if you look at the problem, the last problem here, D, it is how many grams of excess. So I need to change the moles to grams. Up to this point, you see where my cursor key on whiteboard, I'll only get the moles of zinc consumed, but I want to convert that moles to grams of zinc consumed using its molar mass. So basically the last conversion factor is the molar mass of zinc.
Okay, got you. I was confusing the 2 with like the molar mass, and I just totally got what you're talking about. So thank you.
Yes, yes, that's what it is.
I had a question.
Yes.
Would you be able to start the conversion with the 2 gram strip of zinc and then
You say what?
Would you be able, instead of the silver nitrate, would you be able to start the conversion with the 2 grams of zinc and then not have to subtract the excess? Or is this like the only way to get that answer?
If you start with the two, you need to know how many moles of, you need to have another conversion factor to know how many moles you will be using for that. But the best way is to use this approach that this is my limiting reagent, how much will I be using?
Okay.
But if you start with 2.0, this is an excess reagent.
Mm-hmm.
Yet we want to know how much is consumed. If you do that, you'll have to find out how many, what is the mole ratio. You're gonna use that at how many moles of that will be consumed, and still
Yeah.
it will give you how much was consumed out of the two.
Right. Okay. I just want to make sure you could do it either.
Yeah. Any other question? So practice with the end of chapter problems, and somebody asked about the practice. It is at the bottom of the My Mastering assignment. End of chapter problems, you'll see a lot of problems on limiting reagent, excess reagent. Ties up to that, having gone through the limiting reagent, excess reagent is the theoretical yield and the actual yield. From the word theoretical, in theory, it's not possible. You know, theory is something not practical. And theoretical yield, all right, theoretical yield, the way you look at this is theoretical yield is simply from the limiting reagent, or rather amount of desired product you expect from limiting reagent. The desired product from the limiting reagent is theoretical yield, the yield from the limiting reagent. In this example we did before, we identified the limiting reagent. The limiting reagent was silver nitrate. And this is the theoretical yield. We expect in theory to produce 1.59 grams of silver. But when we go to the lab, we are in the lab, there is no way we can get exact 1.59 simply because of random errors. Maybe the instrument we will use to weigh out the reagents, they are not calibrated. When we transfer the reagent from container A to container B, we may lose something in between. Something may get stuck on what? On the walls of the container. Take, for example, liquid reagent. Using graduated cylinder, there is no way you will pour the reagent from the graduated cylinder until it is what? Until it is dry. Something is still gonna be wet, and something which will stick on the wall will retain some of the moles or molecules we accounted for in calculation. So theoretical yield is the yield you expect from the what? From the limiting reagent. We call the other product, okay? You obtain in the lab the actual yield, all right? Actual yield is what you actually produce or what you actually measured in the lab. The maximum amount to be produced. You see here when you say produce from where? Produced from the limiting reagent. Okay. I've seen question, you know, on limiting reagent, you will be asked, what is the theoretical yield when this amount of reagent A and this amount of reagent B are reacted? What is the theoretical yield? That is a question of the limiting reagent. So anytime you see the theoretical yield, you calculate from the limiting reagent, and whatever you obtain in the lab, is the actual yield, From that, the two values we can use to calculate the percent yield. Percent yield is obtained using this equation, and you see from percent yield actual over theoretical yield. All right. Theoretical yield, this is from the limiting reagent. The top part is from the experiment. The bottom part is from the limiting reagent. Sometimes you are given, sometimes you may not be given. Sometimes you are given, sometimes you may not be given, right? Here is an example of a reaction between iron 2 oxide, this is iron 2 oxide, and carbon monoxide to produce 2 moles of iron and 3 moles of carbon dioxide. If you start with 150 grams of iron 2 oxide as the limiting reagent, so what I know is this is an excess reagent. This is the limiting reagent. What is the theoretical yield? Remember what I said about the theoretical yield? You determine from the limiting reagent. Since 1 mole produce what? In this case, you can use either of the product to determine, oh yeah, we are looking for theoretical yield of iron, so we are limited only to iron. You got to use what? The stoichiometry. Mole ratio in the parallel equation, 1 to 2. It does not mean we multiply by 2, the 150 here to get 300. You know, somebody can say, if I have 1 here and I have 2 here, why don't I just say times 2? No, it doesn't work like that. You got to do the right way using the stoichiometry. In this case, this is our limiting reagent, 150 grams of iron or 2 oxide. We use the molar mass to convert. All right. What I'm using here is the molar mass of iron 2 oxide and 159.69. This is 159.69. 159.69. (159.69) grams of iron 2 oxide. To be clear, this is grams. So what I'm doing is converting the grams to moles. Just like before, you got to reconcile the units. Look at the mole ratio. My conversion factor is, I want to get rid of what? I want to get rid of moles of iron 2 oxide. I'm looking for moles of iron. The numbers which goes in there, I'm basing on what I do have here, that for every 1 mole of iron 2 oxide consumed, 2 moles of iron are produced. So that cancel that we are looking for not moles of iron but grams of iron. So the last conversion factor here is mole of iron, and I'm looking for grams of iron, moles of iron, grams of iron, and 55. This is the atomic mass, 55.84. This is 1 mole. The last conversion factor is just the number of the periodic table, atomic mass of iron. Theoretical yield in grams. So we cancel moles and moles. Plugging in your calculator, you should get 104.91, 104.91 grams of iron. This is the theoretical yield in theory. In most cases, theoretical yield, or rather actual yield, is less than the theoretical yield, even though sometimes you may have actual yield being more than theoretical. You may have encountered this, for example, somebody didn't dry their sample in the lab to drive away moisture. You will weigh your sample plus the moisture which shouldn't be there, and then it will weigh more. So actual will be more than the theoretical. So in our case, this is the theoretical part P. If you are actual yield, this is actual yield. What is the percent yield? In this case, percent yield is given by actual, of course, in grams, over theoretical in grams times 100%. Remember to put 100%. Equals to 8 what? This is 87.9, all right, grams of iron over 104.91 grams of iron times 100%. Grams of iron cancel out. And this leaves you with 82.9. This is the theoretical yield. I mean the actual, the percent yield, not the theoretical. There is a percent yield of this reaction. Percent yield, all right? So you need to read the problem, because not always you'll be given the word actual yield, but problems or a problem could be tailored that a student perform an experiment, and this was how much the student produced or the reaction produced this. That means it's actual. To yield, to produce, actual, what you need to pay attention that is going to change. Any question on is that what it is? Let me see my calculator. The 87 point, that was 87 point. Yeah, it is 87.9. That's, you're right, 83.8, 83.8. I forget to put 0.9 in my calculator. I forget 0.9. That is why the difference. Jason, you're right. 83 point what? 83.8, 83.8%. You're not crazy. So it is 87. We put 87.9 divided by 104.9. Yeah, you're right. 83. Yes.
I do have a question. It's backtracking a little bit, but you said we could use, your periodic table and formula sheet and everything. I keep having an issue where when I print off periodic tables, I can't read the atomic weight. The resolution's too low. The one you're going to provide, is it like easily legible, or am I going to have to write those in?
Oh no, it should be legible. It should be legible. That's why I would send it today. It should be legible. In the past, I've never had any situation that somebody could not read. Yes.
Okay.
Yeah. So as part of it, that's why I want to share it today, so that you can look at it. Practice with the formula sheet. You see what I mean? That is what I will share today. So with that, that is what I wanted to cover in chapter 3. Any other question on 3?
When will you be posting the quiz for this, just since the exam is on Thursday?
Oh yeah, it should be available. I'll also make available today. All right. And you can work on it simultaneously. I know sounds like too much pressure, but the semester is rolling out. Today is June 1st. Next month, we're done.
When is the quiz for chapter 3 going to be due because the exam's on Thursday?
I'll make it until next class period, but it's up to you to really reprioritize your agenda so that you can nail it down, before, but I don't want to rush you.
So it's going to be due on Thursday or next Tuesday?
Next Tuesday, but if you can get done earlier than that, you are on the safe zone. Okay? Any other question? If there's no question, let's just shift gears to real quick. And I think this is something you have, we have covered a little bit, as we go along. The concepts keeps on coming, showing up, and the more we go over and over, it becomes just inbuilt, and it's gonna be much easier. And like when we are starting off the first time, some of the terms, some of the technical terms are new to you, but as we go along, we will repeat some of the concept we covered previously. Chapter 4, reaction in aqueous solution. So when we talk about reaction, it is what comes to your mind is chemical equation, balanced chemical equation. What does the coefficient in the balanced equation represent? Chemical reaction. Know where products are. Now, our reaction in aqueous solution is a solution where, all right, the solvent is H2O. Before that, let's see what solution consists of. It is made up of what we call the solute and the what? Solvent. Solvent. This is V, solvent. This constitutes a solution. Solution, we may think that a solute is always a solid and a solvent is always a liquid. This is defined as the major component in a solution. This is a minor component, and you may think that our solution is made up of two things. No, it could be more than two, but the major one is considered as the solvent. The other, if it is more than two, are the solutes. Solution is made up of homogeneous mixture or heterogeneous mixture of solute and the solvent. And a solution where the solvent is H2O is called aqueous solution. By the way, most of the chemical reaction, most of the solution you will encounter in chemistry courses are aqueous solution, which means H2O is used. This is the roadmap what we look at in chapter 4, general properties of aqueous solution. You know now what is meant by aqueous solution, and something like Na, just to give you what this means. I used this before. When AQ is used, it means aqueous solution, and aqueous solution of sodium chloride. So general properties of aqueous solution. Precipitation reaction 4.2, that means when two reagents are mixed, a solid is formed, we call precipitation or a precipitation reaction. Acid-base neutralization, a special type of double replacement reaction where OH, all right, where OH ion combined with hydrogen ion to produce 2H2O. No, it's only one to produce liquid H2O. This is aqueous. This is an acid-base neutralization. We look at in chapter 4, section 4.3 in details the type of neutralization reaction where an acid, all right, where an acid react with a base. 4.4 oxidation reaction is a type of reaction where there is transfer of electrons. So we'll keep track of the oxidation number, how to do that, and concentration. It's an important concept in chemistry. Molarity, that's where we look at the molarity, how to express the ratio of the solute to volume of solution in liters. And dive into the dilution law, okay? And solution stoichiometry, which is basically the same as stoichiometry we looked at before. Let me see, let me ask you, Salina, you asked a question. What topics do students struggle most in or on the first exam? That's a good question. If I looking at what I've just been raising, the critical is chapter 2, writing the correct formulas of either molecular compounds or ionic compounds. It will compound into other topics we just looked at. For example, if you don't write the correct formula for your compound, how will you balance the equation? All right, it's gonna be a challenge. So please, I will stress the stoichiometry and writing the correct formulas for ionic compounds, molecular compound, and acids, keeping track of, the ionic charge. How will I predict the ionic charge for main group elements when I use the Roman numeral? What does the Roman numerals comes in? And if you can nail down that, I think you will be fine. Selena, those are the topics I see that it will compound into other aspects, into other topics, into other concepts if we don't really nail it down, the concept of naming the compound correctly.
Thank you.
All right, yeah, so please be careful with, and if I were you, I'll read chapter 2, 1, 2, and 3, and use the practice question that I know. Why am I not really caring it? And you have a lot of questions on, those practice problems for each chapter will really help you. Like you will cage yourself that, do I really know? I know the due date is end of the semester, but I wanted just to make them available so that you can go in anytime. Jason, you have a question about naming the compound. Rule number 1, think about element 13 through 15. Well, those groups, right, 13 through 15, they consist of non-metals, metalloids, and metals. So probably maybe that is what I mentioned about, you gotta be careful when you get to those groups because they consist of non-metals, metalloids, and metals, even though they are in group they are in group 4, for example. We have non-metal, metalloids, and metals. You got to look at that as well.
I think he's talking about organic compounds, but I think you told us not to know how to name.
Oh, yeah. Organic compounds. No. Yes, organic compounds.
Okay.
Yeah, thank you.
Mm-hmm.
Okay,
Yes,
so I don't have to worry about it then.
Yeah. Don't worry about organic compounds.
Okay.
All right, thank you. Thank you for bringing that. I think that was Lawrence. That was Lawrence, right? Thank you. Somebody, I need to unplug my Alexa. I call Alexa and Alexa was talking to me in my room. So let's see, I've just mentioned to you what constitute the aqueous. When we say aqueous solution, I've underlined the word aqueous solution. An aqueous solution is a solution where solute, or I mean the solvent, in this case is H2O. Solution is made up of two things: solvent present in greatest amount and solutes. And if you look at the plural here with S, you can have two or more solute in the solution formation. This text doesn't go in details about different classes of solution. Air, for example, is an homogeneous mixture of gases. So gas, yeah, that means the solute is the gas, the solvent is the gas, that's gas. And we can have solid, that means the solid is solvent, the solid is the solute, such as in alloy, alloy, two metals blended in to form one homogeneous solution. We can have liquid, that means the solution is made up of a liquid solvent and a liquid solute. But for us, I want you to differentiate between, or the two terms here. Solvent is always present in large amounts. Solute is present in small amount. And a solvent, all right, doesn't have necessarily to be a liquid. Sometimes you may have it also two of them being solid, but if it's present in using the relative amount, you should be able to distinguish. Now, aqueous solution here is a solution where H2O is used as solvent. When water is used as the solvent, we end up with what we call aqueous solution. So moving forward, all right, next time you see something like this right here, and then AQ like that, or hydrofluoric acid AQ like that, it means it's dissolved in H2O. It's dissolved in H2O. Solvent is H2O. Now, we will now zoom to the molecular level, to atomic level, and see what is happening when, let's say, for example, dissolving an ionic compound versus dissolving a molecular compound. If I look at the diagram you see here, it is an illustration of, dissolving methanol in H2O, all right? If you look at the arrow, this is methanol. And by the way, in chapter 8, we'll see in molecular models that chemists use spheres to represent atoms, and white sphere represent hydrogen and red represent oxygen. In this case, you may see this is the molecular geometry of water with oxygen, with hydrogen there. What is playing a role here is there is, even though I don't want to jump the gun, the partial positive, understand what is going on here. That positive, that means the electronegativity for oxygen is greater than what? Is greater than for hydrogen, and the electrons are pulled towards oxygen. The shared electrons here are pulled toward oxygen. The electrons are pulled toward oxygen, making oxygen more electronegative. Electrons are negatively charged. With that understanding, you will see what happened at the molecular level. At the molecular level in aqueous solution, all right, when ionic compounds are dissolved in what they dissociate, that means it will break. ionic compounds such as sodium chloride like that will dissociate into sodium cation and chloride anion, negative and positive. This is dissociation. Sometimes we use ionization, it's the same thing. But molecular compounds do not dissociate. They just dissolve as molecules. Sucrose, for example, does not dissolve. All right. Sucrose, for example, does not dissolve or does not ionize, but it dissolves as a molecular compound. There are terms which you need to remember. For example, here, what do we mean by solvation? Solvation is a process where the solute, or rather the solvent molecules surround the ions, if it is ionic compound, surround the ions such that they do not combine to form the ionic compound. Using sodium chloride as an example, this is positive. Let me just write that positive. From what I just showed you, oxygen is more electronegative compared to what? Compared to hydrogen. If you look at the orientation, all right, the orientation of water molecule around, all right, around sodium, the association is on hydrogen here, hydrogen here, hydrogen here, hydrogen here, hydrogen here. They surround the sodium cation using oxygen, which is negative. This is negative, this is negative, this is negative, because sodium is positive. If I blew up the other one, let's just go right here. Maybe if I blew it up, if you look at this, this is chlorine. The negative is surrounded by water molecules, and the association is on the hydrogen, which are partially positive. The purple spheres represent sodium cation, and if you look at the oxygen, they surround the water molecule. I mean the sodium. This process by which the solvent surround the solute is called solvation. Solvation, if it's a solvent. But specifically speaking, for, all right, hydrogen or H2O, we refer to that as hydration. We refer to that as hydration if it is only H2O. So here is solvation. For molecular compounds, this is methanol. It follows the same pattern, all right? The same pattern, solvation and hydration. We use the word hydration for talking to only one solvent. Hydration, when you get dehydrated, you lose water. Hydration for water. Solvation is for solvent. Now, there are molecules which ionize in H2O, we call those electrolytes. We need to know what electrolytes are, electrolytes and non-electrolytes. Electrolytes and non-electrolytes. Let me just real quick here, go to electrolytes and non-electrolytes. Electrolytes are compounds which dissociate or ionize completely to form H2O. I think this is chapter 3. I meant to say 4. We are in 4. So electrolytes are compounds we dissociate completely to form ions. Non-electrolytes, they do not ionize. You need to know what constitute electrolytes, non-electrolytes. Electrolytes are mainly, ionic compounds. If I can identify, one way of identifying a strong electrolyte is if it's an ionic compound. You see here, they are stronger electrolytes. Weak electrolytes, you see, we don't have weak electrolytes, we don't have weak electrolytes. That is for ionic compound. For molecular compounds, strong acid, this is where you will need to memorize. In Chem 2, all right, you'll be required to memorize or to recall what you learn, what we are going through right now in terms of strong electrolytes, weak electrolytes. Strong acid, weak acid, look at table 4.2. Weak acid are what? Weak electrolytes. And how do I know weak acid? Acetic acid is an example. Non-electrolytes, all other compounds are non-electrolytes. So if I know what constitutes weak acid, look at table 4.4, I mean 4.2, what constitute the weak acid. So how do I know that this is a strong electrolyte? If it dissociates, you don't have to look, you don't have to perform the experiment and say, oh, it did dissociate and therefore this is a strong electrolyte. All I know is if I learn in chapter 2 that this is an ionic compound, which you should know, then you know this is a what? Strong electrolyte. You should be able to identify where it will dissociate. What ions will be produced when dissolved in H2O? What ion will be produced when dissolved? Non-electrolytes, when dissolved in water, it will not dissociate. That's one way you can look at it. There are some experimental setup you can do. For example, you see here, there are some experiment you can perform to test whether a solute is an electrolyte. Sugar or sucrose, non-electrolyte, even though it dissolves, it does not produce ion. But strong electrolytes such as stable salt will dissolve, it will conduct electricity and you will see the bulb light. Look at the solution, aqueous means it dissolves. Look at this, AQ, it means it dissolves. You should be able to tell or identify strong electrolyte. You can be given the formula or given an example on that. Let's see, there's an example on identifying strong electrolyte versus weak electrolyte. Strong electrolytes dissociate completely or ionize completely to produce ion. HCl is a strong acid. It dissociates to produce hydrogen ion and chloride ion. weak electrolytes such as acetic acid. This is a common acid you will see. It does not dissociate completely. You may see there's an arrow I missed here. There should be an arrow here. What this means is if we have 100 molecules of acetic acid, only 5 molecules will dissociate to produce hydrogen ion and acetate ion. 95 will remain as molecular compound. There is a confusion in the sense that you may think that why is this equation, the top one here, the same as this, yet we consider the later one, this one is weak electrolyte, yet this one is strong electrolyte. What this means is the later one, acetic acid, does not, all molecules, and I gave you an example that if we have 100 molecules of acid, only 5 of them will produce these 2 ions, hydrogen ions and acetate ion. The rest of the 95 will remain as acetic acid. It will remain as a molecule. Whereas if we have 100 molecules of hydrochloric acid, all 100 will dissociate to produce hydrogen ion and chloride ion. That's the difference between strong electrolytes and weak electrolytes. In this case, weak acid. And there is dynamic equilibrium. You will see in Chem 2, in details, there is a chapter specifically dedicated to chemical equilibrium. That means the reaction is going back and forth. Let's see, question is, which solute will cause the light bulb to glow most brightly? Let me just see how you will respond to this. Which molecule will produce? Let me see somebody look at that. Which molecule will produce? The correct answer is yes, Lauren, sodium hydroxide. Alex, sodium hydroxide, that's correct. It's because if you look at the, all this you see here, B is the ionic compound. This is, methanol, acetic acid cannot be identified. This is the only ionic compound, and it will call for what I brought to your attention, that you don't need to perform the experiment to say, oh, this light will bulb. How will I know? It's by the fact that all strong electrolytes will ionize, and the only ionic compound in these 3 multiple choice, this is the ionic compound. That's what I look at. So up to that point, before we look at the solubility of ionic compounds, you need to know what constitute what we call strong electrolytes and what's meant by strong electrolyte, weak electrolyte. Okay. And tied to that, back to ionic compounds. Remember what we talked about in chapter 2. Ionic compounds are made up of metal and a non-metal, or metal and polyatomic ion. Not all of the ionic compounds dissolve. Some of them do not dissolve. Okay, there are 10 solubility rules you are expected to remember, but I'll give you a table which will help you out in summarizing the table 4.1 here. There is a table, let me show you where it is. In terms of solubility, you can go ahead and see, all right, if All right, when we get to metathesis reaction, instead of memorizing all these, that nitrate will form, none of them will form insoluble. That means all of them are soluble. All acetate, any ionic compound with acetate ion will dissolve in H2O. All compounds with nitrate ion will dissolve in H2O. All what you read is all compounds containing chloride are soluble except silver chloride, except mercury 2 chloride. I mean mercury 1. This is mercury 1 chloride and lead 2 chloride. These are the exceptions. So that's how you read this. All chlor or bromide containing compounds are soluble except, you see this? So you read this as iodide. All compounds containing iodide except silver and all these. All compounds containing sulfate ion except strontium, barium, mercury 1 ion, and lead 2 ion. That's how you read these solubility rules here where we're going. It's gonna help us when we get to the double replacement reaction and writing the net ionic equation. So knowing these compounds form, gonna be using this in the next section on the molecular equation, complete ionic equation, and net ionic equation. So how you read this is all compounds containing sulfide, SID, except those containing ammonium ion, alkali metals, which you know these are group 1, and calcium, strontium, and barium. You know alkali, these are group 1 metals, group 1 metals, group 1 metals. So all hydroxide. This will help you in writing the physical state of your product. Whenever you are mixing two reagents, we'll have to indicate whether it is solid, whether it is aqueous, whether it is solid, whether it's aqueous. Testing you on solubility, what when dissolved, or what dissolved species are present in a solution of potassium cyanide. This will call for, identifying this is a ionic compound with a cyanide ion. We call this cyanide. It calls for, chapter 2 polyatomic ion, most common polyatomic ion cyanide. So there is no way you will break between, split between carbon and nitrogen and say, no. It's just about knowing that this compound is an ionic compound, and where is the cation, where is the anion, where is the polyatomic ion? So the correct answer here is D, potassium ion and cyanide ion, and we are given the physical state aqueous. That means going to be in physical state.
So were you saying that we do need to memorize all of those rules, or did you say that you'd be giving us like a chart to go off of on the test?
Yes, I'll give you a chart to go with that. I'll give you a chart, and I'm going to show you in a moment how we are going to use that chart. But it's good to know both ways. It's just like knowing all the roads in our neighborhood, that which one is shortcut to get to point A to point B. So with that, I've shown you what the text expects you to know from table 4.1, but the table I'll give you might be handy. And this will be helpful in precipitation reaction. You know what precipitation reaction? A reaction that when you mix two reagent, one of the product is what? Is in solid state. How will you know that this is a solid? Let me see if I can minimize and show you, but before I show you that, precipitation reaction comes from the word precipitate. A precipitate is a solid formed when you mix two reagents and one of the product is solid. Here is lead 2 and potassium iodide, lead 2 and potassium iodide. Let me see if I can, using this as an example, I'm going to minimize this, use my whiteboard. I want to use my whiteboard to show you what that, I'm using my whiteboard here. This one is the one we were looking at was lead to nitrate, and it is aqueous plus potassium iodide. The question is in precipitation reaction. I don't know whether it is even precipitation. I may not be given that. But you need to translate, which goes back to chapter 2, the chemical formulas of, and by the way, this is also aqueous. The chemical formulas of your reagents and predict the product. In this case, I'll write that the lead to nitrate is this is what I do have, aqueous. How do I know that? It's because of lead 2 is positive 2 and nitrate is -1. That is the correct formula for lead 2. And by the way, there's a 2 here. Using the crossover rule, how I ended up with that. It is not just putting them together. You know, somebody might say, let me just put it like that, NO3 like that, and say, I have lead 2 nitrate. Or maybe even putting a 2 there as a subscript. No. You have to play by the rules. So that is the correct formula for what? For the first reagent. We are reacting with potassium iodide. Potassium iodide is Ki, and it is aqueous. Remember, potassium is in group 1, so it is +1, and iodide is in group 7. This is chapter 2 concept, right? Using the periodic table. Using the periodic table, there is lead 2, and using the Roman numeral, we know the charge for lead is. Nitrate is polyatomic ion. This nitrate is polyatomic ion. The question is, what are my products? The author expects you to be provisioned to commit your memory the rules given to us in table 4, all right, in table 4.1. But what I don't know if you can go with that, but what I said is I'll give you a table, and this is what you will assume. Assume that you have a reaction container like that, and ionize or look at the ion. This is double replacement reaction. These are the ions from the first reagent. These are the ions from the second reagent. See that? We don't know which one is solid. And if they are switching the ions, this means lead will combine with, lead 2 ion will combine with iodide, potassium will combine with nitrate. If I know that, I'll write the correct formulas as lead to PPI like that. Still, I don't know whether it is solid or liquid. I don't know whether it is, I don't want to, you know, plus KNO3. I'm getting these formulas from this. If I don't write the ionic charges, I'm using that as a container that I'm mixing the two. Let me just have plus right there that I'm mixing the two reagents. I need to know the ion from reagent 1. I need to know the ions from reagent 2. okay? So the author expects you to memorize that when when lead 2 combined with iodide, will it be solid? Will it be, when nitrate combined with potassium, will it be aqueous? Anything soluble will be aqueous. So with that, in order to identify the physical state of the product, I will, let me just minimize this. And what I'll do is show you on the periodic table. This is the solubility chart, and it is on available online. Let's download this, and I will show you. It works maybe 97%. All right, it will work 97%. That you will now combine. Look at the ion in question. That led to, when it combines with iodide, you see this iodide and lead, where it combines here is solid. So anything solid means it is insoluble. So I know my product will be solid. Instead of this, you can memorize table 4.1. So I know lead to iodide is solid. And by the way, I didn't put the 2 there. I'll go back again and give you, I forget to put the 2 there. So it's lead 2, if you're right, taking notes, lead 2. If I look at the word potassium, we may not have potassium, but we know it is in group 1. I don't see potassium here. But group 1 here, all group 1, I can just use this and say, where is nitrate aqueous? And if I see anything on nitrate right here, they are all aqueous, so I know it is aqueous. This table is online, and with that, here, I know now this is what? This is solid, and this is aqueous. It is important that you write the physical state of the product. This is important for getting to net ionic equation, total ionic equation. So up to this point, I have written down the correct formulas of my product, but I'm breaking the rule of law of mass conservation. We need to balance the equation. We need to balance the equation. At this point, you won't be told, you are expected to know that all equations should be balanced no matter what, to obey the law of mass conservation. For example, here, we have 2 iodide, we have 1 here. We have what? 1 nitrate, you can balance polyatomic ion as 1 entity, and therefore, we need a 2 in front of potassium nitrate. We need a 2 in front of potassium iodide and potassium nitrate, and the equation is balanced. The equation is balanced. This is precipitate. What you see here is PPT for precipitate. This is precipitate like that. This is a precipitate. You see that? A precipitate will fall out. So at this point, you will not be given, chances are you will only be given the reagent, and you are expected to predict what? The product on the other side. It is double replacement reaction. If this is for the beginning, use this illustration. This is the roadmap I've always used to predict the correct formulas for my product. Once you identify the correct formulas of your product, you do what? You balance the equation. You balance the equation, and please indicate the physical state of your what? Of your reagents, of your product, if it is liquid, if it is aqueous. Using that table, I'll allow you to use in the exam, and you can use in the homework as well, so that you predict what? You predict the correct formulas of your product. So here, all right, here is, all right, here is the equation, which you don't need to memorize. I was just showing you on the chart. This is what I was showing you on the chart. The balanced equation, how did we arrive here instead of just memorizing? Look at the equation for this precipitation reaction. Lead 2 nitrate reacting with potassium iodide to produce 2 moles of potassium nitrate aqueous and lead 2 iodide solid. This is the precipitate. This is the precipitate. You can use the table. You can use that chart I gave you. It is available online to predict precipitation reaction. Predict precipitation reaction. So that's what I want you to know, how to predict precipitation reaction when you mix two reagents. When you mix two reagents, you got to know which ions are present. All right. In an equation, ions, it could be monoatomic, it could be polyatomic ion present in the what? In the reagent. Remember that cartoon I showed you? We were able to see the nitrate ion, the cation, and the anions. So consider possible like double replacement reaction. It will help you in identifying the product. So either table 4.1 or you can use the chart. The chart is available. You will print out that. If I look at the magnesium hydroxide, when you mix those two, how to end up with this, you don't need to memorize. That's a bad strategy. It's knowing the concept. You know, somebody will think that, oh, let me read, and the instructor might give me question on magnesium nitrate and sodium hydroxide, and I should know that it will form this kind. If I tweak a little bit, if you don't know how to use the chart, if you are not well-rounded with the solubility rules on table 4.1, chances are you will miss, and that's not the way forward. Any question on using the solubility chart? So metathesis reaction, which you will see often, or you may have seen this, it is just a double replacement reaction I walked you through. It is double replacement reaction where the ions are exchanged. You can think of the cations being, or cations swapping the anions. You saw our lead combined with iodide and potassium combined with nitrate. They swap the ions. In this case, magnesium, which is a cation, and sodium, which is a cation, they are exchanging the anion. Hydroxide will combine with magnesium and nitrate will combine with, but of course you have to play with the rules of writing the correct formulas and balancing the equation. Writing the correct formulas for ionic compounds, that is chapter 2. Balancing the equation, that is chapter 3. And then metathesis reaction, this is chapter 4. You see how they are just compounding. If we miss chapter 2, chapter 3, and then we are in 4, we gotta know all those steps so that it's going to help us in writing the correct formulas. Write the correct formulas. Write the formulas for the product. How will I know? Please use the table. There was a cartoon I used earlier on. Please refer to that, where the ions, in order to write the formulas for, and remember we are using the crossover rule in swapping the what? The ions. Use the charges. All right, use the charges to write the proper subscript. If you need to use the subscript, you need to know that. Solubility rules allow you use the word, use the chart to predict your product, and then balance the equation here. This was chapter 3. balancing the equation is the last thing you want to pay attention to. Balancing the equation is the last thing you want to look at, all right? I don't want to start over this concept. We will look at next week, not Thursday. I want you Thursday come prepared for the exam. You need to join the Zoom. I'll let you how long the exam will take on that day. There will be no lecture on Thursday. You'll only have to take the exam and leave, just for, you know, people who are eligible for extended period of time. I don't want anybody to lose time that are, you know, rushed, that give lecture and then expect them to catch up on their own. So Thursday we'll only take the exam. Do study the best you can. I don't want you to, you know, go back again. Use the practice questions. And there will be SI support. There is SI session 6 p.m. today. Please show up again. Nick actually posted an announcement brought to your attention. Other than that, yes, the exam will be on Lockdown browser. If you have a problem with Lockdown browser, please uninstall and install again. If you have a problem with Lockdown browser, please uninstall and then install again and see how it goes. Other than that, the class is dismissed. We will meet again on Thursday. Yes, I'll be, we will have to join Zoom just in case something happened. I'll get back with you right away. The exam will be during the class time, not outside the class time session. Other than that, any other question?
How would we join Zoom on Thursday if we're going to be taking the exam? Because the proctoring won't let us do that.
It will not, okay. If not, we will just have to join and then answer the question you may have, and then we'll take it from there, okay?
Okay.
All right, just to make sure that we are all on the same page.
So we only need to join Zoom on Thursday if we have a problem with the exam.
No, you'll have to join in and maybe somebody asks a question. If not, and then we go out and then I'll let you take the exam. Just the way we, you know, I make announcement, just in case somebody says that I have a question on this, I should be able to address before that, which will be like 10 minutes or so. And then we break it.
Okay, so we still need to join at 10:50 on Thursday, but it'll only be for a few minutes and then
Yeah,
we'll
for a few minutes, and then yes, make sure that, you know, everything is okay. Say, hey, you know, the exam is available now, you can do it.
Okay, thank you.
All right, thank you.
Thank you.
I'll see you on Thursday. The class is dismissed. Have a wonderful afternoon. Thank you.